Guys, so let's continue on with the remainder of this lecture. So now what we're going to do is we're going to talk about how we synthesize membrane components, and then essentially the last part of this, which is membrane transport. So as we talked earlier, the main component of the membrane is the phospholipid. And so essentially, in eukaryotes, the cytosol, which if you remember, this is the liquid part of the cytoplasm, right? And the endomembrane system work together to synthesize and transport the lipids to the part of the plasma membrane. If you remember the endomembrane system, that's the one that starts with the nucleus, and that gives information to the rough ER, right? Along with, and on the rough ER, there's ribosomes, and they basically make proteins, right? And then essentially they shuttle them through and go into a vesicle, then they go to the Golgi, and then essentially go back into a vesicle and move to the basically export things to the extracellular matrix or to essentially lysosomes. And that, if you don't remember, go ahead and look at the last lecture. Towards the end of that Unit 4 lecture, it talks about this. And so essentially what this means is the fatty acid tails of the phospholipid, because this is what we're talking about here, phospholipids, right? Which are basically the main component of the plasma membrane. They're made versus enzymes in the cytoplasm, right? And then essentially and they're taken from cells into cells from food. And so that's where we make actually the building blocks. And then the actual part of putting them all together is the rough ER. So essentially this is where everything that's in the cytosolic leaflet of the plasma membrane is essentially processed or made by the smooth ER. You know, we talked about rough ER, but just replace that, and then we're talking about the smooth ER. Now, with the lipid bilayer, when it's actually made, it is essentially what's called flexible and self-sealing. So it's the idea that you may have, actually, let me redo this again so that it looks a little bit clearer. So essentially what we can have here are these heads. So these are the polar heads and the non-polar tails coming together, right? And all they're saying is if we have some kind of stress that comes in, as in something pushes, you have force or something pushes here, right? Or we are essentially going to make a vesicle and the vesicle is going to kind of butt off and leave here, that essentially what can happen is that these guys can move and open up here and allow the thing to essentially move through it, or to basically, if it pushes that, it could push through this, and as soon as that force is gone, essentially all of this leaves and it fills back in. It's the idea as if you've ever seen anybody bob for apples, that essentially you have this whole thing, this whole kind of barrel full, and the little apples are on the top, right? And they're floating around in the water. And someone takes their head, right? And they pretty much go and they put their head into the apples and they push the apples normally to one side and the next. And then once they put their head back up, then essentially those apples fill back in. It's the same idea as if you go to the beach and you're trying to dig a hole with sand, that as you're digging the hole, more sand comes in to replace it. So that's what they mean by self-sealing, and that it's flexible, is that you can move it around. the lipid bilayer are confused with other membrane. So this is the idea. If you have the plasma membrane over here, you can have a vesicle come and it'll move over and it will fuse with this membrane essentially to dump stuff out. And like I just said, it forms vesicles. So if you have essentially the rough ER or an ER over here, essentially the end of it will kind of bud off so that it can leave as a vesicle. Now, how we synthesize proteins or transmembrane proteins is essentially it goes through the ER membrane first. And then from the ER, it becomes part of the actual vesicle that it's going to move to the next thing through. So if you look here, right, the very first protein synthesis actually is starting to begin. So if you look here, this is right here, this is basically what's called RNA, which is basically DNA makes a photocopy or kind of a copy of itself. It's not an exact replica, but it makes a kind of copy that can leave the nucleus because we don't want to destroy our DNA. And then essentially RNA comes out, and so this is happening in the cytoplasm, right? And so that's the instructions that the ribosome gets. And the ribosome will start making the protein, as you can see here. And then essentially as it's making the protein, it's connected to the rough ER or the membrane of that. And so essentially it starts making it, as you can see, it starts synthesizing into the rough ER. And then you have this protein here that's essentially holding on to it, right? And so what happens here is that the hydrophobic part of the protein basically gets stuck here in the middle of the membrane, right? And the rest of it threads out because this part is going to be hydrophilic. And then essentially once that whole protein is completed, right, then this little thing that's helping, this protein that essentially is helping it, goes away, as you see here. And then the transmembrane part is stuck. And then this whole thing is going to be part of a vesicle, and that vesicle is going to move to wherever we want the protein to go. So that's essentially how we make proteins that are embedded in membranes. Now, the proteins that we make can be there to help transport stuff around. So we're going to watch a video at the beginning, or we've already watched a video, depending on how far you've gotten in this class, that's going to show basically basically a big vesicle with a motor protein walking on it down these big microtubules. And so proteins are important in transporting materials because that motor protein helps to get stuff around. Of course, it acts as receptors and receivers. So if you have a protein in a plasma membrane, it's on a cell, it can attach to some chemical. And so if it does that, it's going to receive it and then it can bring it into the cell. Or it's going to attach to some chemical and then do some kinds of change to it. And that's what enzymes do. Proteins are also important in cell recognition. So if you've ever heard of basically antibodies, they help to recognize things on the outside of cells called antigens. And these guys are proteins. So when you get sick and you have this little bacteria, right, that comes into your body, essentially it has little things attached to it called antigens. And that basically these things called antibodies can go in and recognize them and say, hey, this is a bad protein. let's get away from, basically get rid of it. And then you take white blood cells and it's like, and they kill it. And then essentially they can structurally link stuff. So remember when we talked about gap junctions, desmosomes, and tight junctions? As a reminder, remember gap junctions let ions and molecules through it. Desmosomes were the molecular Velcro that helped put cells together but gave it some flexibility and movement. And tight junctions are really tight linkages between cells that basically don't let any kind of things like fluids or stuff between them. Now, each one of these are protein structures that essentially are linking cells together. Now, what do cells look like? Or proteins look like? Well, this essentially is a transmembrane. It has what's called dual solubility, which means you have parts that are polar and parts, as you can see here, that are non-polar, right? So as you can see, these are basically what they really look like. There are these long strings of amino acids that kind of curl together here. And I'm just doing this so that you guys can get an idea. And essentially, they make these kind of circular structures like this. And so on the outside here, all the way through this guy, it is hydrophilic. But this area here on the outside that's exposed to these tails are hydrophobic. So because they can interact with those two kinds of molecules, it's considered dual solubility. So now that we know how those membrane components are made and how they're arranged, let's talk about how they actually work. So membrane transport is the idea of allowing things to go through. But because the membrane is structured the way it is, it has what's known as select permeability, which means they're kind of like a bouncer at a bar. It only lets certain people in. Right? So because the plasma membrane has hydrophobic parts of it and hydrophilic, it's going to interact. So it'll allow the passage of some ions and molecules, but not others, right? And this is important because this is going to be what allows to control the volume and the internal composition of the cell. And it does this by only allowing the particular certain ions or molecules into the cell. So this is going to assure, one, only certain molecules enter, that if you've made these what are called metabolic intermediates, as in these molecules that we've only halfway made, that they stay in there. Like if you essentially are trying to make a dollhouse and you don't get it all done in one day, right? And you basically have just painted your doors and you've made windows and you've made kind of, separate walls. You don't want to come home and find that someone's thrown all these away, right? Where you have to start it all over again every day. You're going to put these in a safe spot so that you can keep working on them. And you're going to build more of it and put it together a little bit at a time. So basically, metabolic intermediates are, okay, we are going to want to make stuff for energy later, or we're going to want to make stuff to build stuff later. But maybe we haven't done everything with those molecules that we need yet. So we want to make sure they stay in our house or our cell. So it's the same thing as making sure that your doors, your windows, and your walls stay in your house, in your hobby room, so that you have them for when you want to continue building on your dollhouse, right? But at the same point, if you've made your door and there's all kinds of wooden waste left, right? Or fragments that you don't need, you want that to go into the trash. So if you have waste products you're done with, you want the cell to be able to get rid of those or move them to someplace else. So that's what the membrane does. So as you can see, these guys have high permeability, and this means they can move through the cell or through the cell membrane, right? So you have gases. Gases can get through very easily. You have ethanol, which means it's a neutral molecule, but more importantly, it's small, right? Uncharged is what it means. So, that's important. Here, we have what's considered moderable permeability. So, they move through it, right? But it's at a medium pace, right? So you have molecules like water that it is polar, but because it's small enough, it can move through. And the same idea is with the waste product. This is waste, right? Known as urea. Now, these guys have low permeability, which means they move, but super slowly. So these are the ideas. So because these don't have high permeability, most times what you're going to do is you want proteins to help move them faster. Right? So in this type, this is going to be polar organic molecules like sugar, right? They can move through, but because this right here is nonpolar, it's slow. But these still are small, right? So if you want your this guy right here, if you need sugar to come in quickly, this is not going to be a good idea for this to happen. So you are going to have here channels that they go through. So for instance, diabetes is the idea that sugar can't get into your cell for you to essentially make energy. And even though sugar can go through slowly, it's not at a high enough permeability for it to be effective. And these have low permeability, which means, yeah, they're pretty much locked outside. And so here you're talking about amino acids, ATP, proteins, large sugars, DNA, RNA, and stuff that's charged. So these guys need proteins to get across, or AKA channels to get in. So you have two types of transport. You have what's called passive and active. If you're being passive aggressive, it means that you're not really doing anything directly. So this means that it's like relaxed, no extra input. Active, if you're being active, it means it takes energy for it to happen, right? Passive, no energy really. You're just sitting on the couch. So these are the main two types. And if you look ahead, these are both passive transports, what are known as diffusion and facilitated diffusion. And then active transport, you can see, takes energy right there. So really quick, what is diffusion? It is the movement of molecules or substances from high concentration to low concentration. And it does not take, the big word here, energy. So from high to low, no energy. So when we're talking about ions or molecules moving in a solution from high to low, we are talking about solvents in a solution, in solutes in a solvent. So what are solutes and solvents? Well, a solvent is going to be something that can dissolve things. And the things they dissolve are solutes. So here we're talking about like molecules, things like dyes, right? Or you can even think about sugar sugar or salts when we're talking about things that can be dissolved. And when we want to talk about these things, essentially, these things that can be dissolved are called solutes. So solutes are molecules that can be dissolved in a solvent. And the last part of this is what are solutions? And solutions are just solutes plus solvents, right? So watch this video really quick to look at basically diffusion, and then we're going to look at the diffusion of water. So, diffusion is just taking something at high concentration here and then essentially moving to low concentration. And this makes sense, guys. If you are packed in a room and there are a lot of these people everywhere, right? And you are just packed to the rim with people. You essentially want to have your own space. You want your own breathing room. So if there's open space in this part of the room, you're going to naturally walk over to the open space, right? So think about molecules in the terms of people, right? You have this really big concentration of people here. And then as there's all this room over here of open space, they're going to move until every molecule or every person has the same amount of space around it, right? Becomes distributed equally eventually, and it's just randomly throughout the water. Now, this happens essentially because the molecules around it, basically, we have what's called Brownian motion. And this is random movement of molecules. So this sugar cube that's here, right, is being placed in a solution of water molecules. And these water molecules are just moving around, right? Think about how people are moving around in a mosh pit. There's no logical sense. They're just moving and they're knocking into people every which way. And so I like to think about this whole process as this random mosh pit of molecules just bouncing around, and they're bouncing off in different directions. And you honestly don't know where they're going to go until, unlike a mosh pit, everybody has a nice amount of room around them for which these solid molecules aren't bouncing into each other. The water molecules still are hitting on them, making them move in these random directions. So this is essentially how diffusion works. And so passive diffusion is this idea here. If you look, you have these molecules. Oops. You have this molecule here, and it can fit through this little pore or hole in the membrane. So he just moves from high to low. And they are going to keep moving until what's known as equilibrium is reached. And do you notice there's a word equal in there? There's a same amount of molecules on both sides. And so essentially this happens, this is the passive of two molecules on the bottom. That was just one. And as you see, they're looking at those, the purple, and you have the red. And so essentially they're going to have a net diffusion this way. The purple is. The red essentially is going to have a net diffusion this way, right? And they're both going to work until they get an equal diffusion, or they have an equal amount on both sides. So this is what's known as passive transport. There's just a door open and they're going to go. No energy required. No energy. That's important to know. And so I'm going to leave this for you, and then we are going to come back here in a second for osmosis. Sorry, guys.